Welcome everyone to my course Formal Methods for System Verification. In today's class, we will start discussing on propositional logic. So, when you take any logic, you first understand what is the syntax of that logic and the semantics of the logic. So, we will start with the syntax of the propositional logic. So, in propositional logic, we have already discussed in the previous class that you basically have only the propositional constant or the Boolean variables in loosely speaking, right. So, if you look into the syntax means how do you effectively write the formula which is syntactically correct, right. So, there is no, it is a correct propositional formula, right. So, in Boolean propositional logic you have basically true and false, right. So, you have true and false which is called the truth symbol, and it has only has the propositional constant, or you can say Boolean variables, right. So, you have individual propositional constant like p, q, r and all, and you have the logical connections, the Boolean connectors, logical connector like say not, and, or, implication or by implication, right. So, now we define atom is basically the minimum unit of the formula, right. So, you should remember this terminology closely because I am going to use them in subsequent classes as well, right. So, atom is basically the minimum unit of the formula, which is basically maybe true, false or the constant, propositional constant, and literal is atom or its negation, right. So, that means p, q, r, similarly not p, not q, not r, right. So, these are literals. P, q, r is basically atom, right, or true, false, they are atom, and literals are atom plus their negation, right. So, we build the formula which is basically a connection, logical connections between these literals, right. So, individual literal can be a formula, or a logical connection between two literals can also be a formula, right. This is how we build the propositional formula. So, some of the correct formula like say if you have say two formula f1 and f2, if you connect them, this will also become a formula, right. Similarly, not of f, and then f1 or f2, f1 implies an f2, right. So, this kind of, these are all correct formulas, but if you write like say a, b and, this is not a logical formula, it is not connecting two atom or two formula properly, right. So, these are the say not b, a, these are not correct formulas, but if you write a or b, not a, b, these are correct formulas, right. In syntax, whenever multiple operator, you need to also decide the precedence of this operator, that means which has the more priority, right. So, the order is this, the highest order is effectively the negation followed by and or, then implication, then by implication, right. So, once you have a formula like this, because this negation has more priority over and, so this means this. But whenever you have formula like this, because and or has the same priority, so you cannot be sure which one to be picked, right. So, you can pick and this and this, but essentially these two are not equivalent, right. So, if you do that, construct the truth table, you will see they are not equivalent. So, in case of same priority formula, you need to give parenthesis whether you want this or that you have to decide, okay. Similarly, whenever have the p implies q implies r, it can be this or this, right, but they are not equivalent, okay. So, in that again you have to decide which one is you need, and accordingly you have to parenthesize when you are using the same precedent logical connectors, okay. Now, I will move into the semantics. Semantics is basically the interpretation of the formula, okay. It means what this formula means, okay. So, for semantics you need basically the assignment of the values to the propositional constant, right, and that is called interpretation. So, you basically have the domain. In my domain, this is Boolean domain, the value can be 0 and 1, and you have to assign the truth value. Remember here, truth value does not mean I am assigning truth value means true to every variables. Truth value is basically true or false, both are truth values, right. So, I have to assign this true or false to the propositional connections, and also I need to know the meaning of this logical connector, which we are mostly aware of. So, once you do this, you will get the value of the formula, the meaning of the formula. The formula can be evaluated to true or false, right. The meaning of the logical connections are well known, but just for completeness I am just discussing. So, if you know there are two variables and if you do P and Q, it is effectively whenever both of them is true, the output is true, otherwise this is false, right. If any of them is false, this is false. For or, if any of them is true, then it is true. It is false only both of them is false, right. So, these are all well known to you. Implication is that P implies Q, that means whenever P is true, Q must be true, right. So, then it will be true. If P is true but Q is false, then this is false, okay. And whenever P is false, I do not care about Q, it will be always true, right, because it says that if P true, then Q true, but if is P false, I do not care about Q, right. So, then P implies Q will be true. So, in general this P implies Q is nothing but not P or Q, right. So, this is how you also can remember. By implication, if both are true, right, P implies Q and Q implies P, it means whenever both of them are same, then only it will be true. Whenever they are different, true and false, it will be false, or false or true, it will be false, right. So, these things you know already. Similarly, the negation is, if it is true, the negation will be false, if it is false, negation will be true. So, if you know this, given a formula say this, I can identify the interpretation, right. So, so PQ I know, I can find out the not Q from this, and then I can do the or P or not Q, and I get these values, right. So, this is how I can interpret a formula of any length, right, by just giving the meaning of the logical connections, okay. So, now let us say I have this formula. Usually the question that we are going to ask is the formula is satisfiable, right. What do you mean by satisfiable? That means there exists an interpretation under which the formula becomes true, right. So, there exists an interpretation there exists an interpretation such that I satisfies the formula. So, this is basically satisfies, right. Now, in this formula I have two propositional constant P and Q. It can have 4 values. Let us say I have taken P is true, Q equal to false. So, if I assign these values to this variable, say P equal to true and Q equal to false, I can identify what is the P and Q, which will be false because this is true and false. What is the value of P or not Q, which will be true because P is true. So, the formula is this implies this, right. So, this is false implies true, and in this case false implies true. So, this will be true because this part is false, right. So, under this interpretation the formula is satisfiable, okay. And this is how we denote. I have already talked about that whenever some interpretation satisfy, I will write this way, and it does not satisfy, it does mean what? Under this interpretation the formula is false, then I will write this way. So, we have learned the syntax and semantics of propositional logic. Now, we will see the decision procedure of propositional logic, which we have talked about, that how do you check the satisfiability of the propositional formula, okay. We have discussed what is satisfiability of propositional formula, right, which is basically says that there exists an input for which, or interpretation for which the formula is true. You can have two different techniques which can be proved by enumeration or proved by deduction. Enumeration, you understood that if I give the formula, I can identify what is the possible inputs and I just evaluate for each possible inputs, right, and then I see whether the formula is true or not, right, which is quite easy, right, which you have already discussed here, right. So, this is one interpretation under which this formula is true. It can happen that this under this formula is not true, but it false. Then what we can do, we can take the next interpretation and check. If it is false there, I check the next interpretation and check, right. So, this way we can actually enumerating all possibilities and check. Obviously, this is not a good method, right, because in worst case you have to check 2 to the power n possibilities, right. So, and there is no intelligence we are learning from one set of evaluation, right. So, the other technique called proof by deduction, where we have certain rules, right. So, some of the things is obviously true in propositional logic and we can use them to prove that certain formula is satisfiable or not, okay. So, to explain this proof by deduction, I will take a simple encoding example. This example has two purposes. First thing is that given some English language logical statement, how do you encode them as a propositional logic? That is the first thing we learn. And then once you encode that, how I can use the deductive proofs to show that whether the formula is satisfiable or not. Okay. So, it is a very simple example. So, here I have three English test statement and I have to check whether they are actually consistent or not, right. The first one says that if x is prime number greater than 2, then x is odd. Okay. So, if you know the prime numbers other than 2, all prime numbers are actually odd, right. That is the first test statement, talks about that if a prime number greater than 2, it is effectively an odd number. And then the second sentence shows that it is not the case that x is not a prime number greater than 2, right. What is essentially saying that some x, which is effectively saying that it is not the case that, so there are two nots here, right, not the case that x is not a prime greater than 2. So, it effectively means that x is a number greater than 2, okay. And then you are saying that x is not odd. So, clearly these three statements are not true together, right, because you are saying that x is greater than 2, x is a prime number greater than 2. So, this must be odd, that is the first sentence said, and then you are saying no, x is not odd, right. So, then that means this cannot happen. So, this is basically if you encode these three English sentence, eventually this should return unsatisfiable, right. So, it basically it is false under all scenarios. Okay. Now, we will see how do you model this using propositional logic. So, to model this I need only propositional constant, right. So, what I will do effectively, I will see the part of the sentence which can be considered as a propositional constant. Okay. So, what I can do, I can say that x is a prime number greater than 2, let us say this is my one propositional variable representing by a, and x is odd, this is another phrase which is encoded by a propositional constant, say b. Okay. If I have these two, I can model all three of them. Okay. So, then how do I model the first one? First one is say a implies b, right. So, it is saying that if x is a prime number greater than 2 is a, so if a then x is odd b, right. So, a implies b. So, by this way I can encode the first statement, right. The next one is quite easy. It is not the case that x is not a prime number greater than 2. So, I have x is a prime number greater than 2, which is a, and it is a x is not a prime number greater than 2. So, not a, and this is not the case. So, this not is this, right, and then not the case. So, it is not a, right, and C3 is quite simple, x is odd is b, so it is not b, right. So, I have now encoded these three sentences using propositional logic. What I have to check? I have to check is f, which is so f is effectively C1 and C2 and C3, right. So, and all of them should be true. Is f satisfiable, right. So, this is the question. So, because in this particular cases I have only two propositional constant, there are four possibilities. You can actually construct the truth table 0 0 0 1 1 0 and 1 1, right, which is a and b, and you can actually check whether the formula is true or not. Okay. You will end up saying that, see for example, you have to have this, right. So, whenever is b is true, this will be false, right. So, this is false automatically because this is and of all of them, right. And then because if b is true, then not b will be false. So, automatically these two are false. And now if you see this is effectively a, if a is false, then it will be false, right. The only scenario is this. So, if a is true and b is false, this will be false, right. So, effectively you can see that it is the formula is false under all cases, and hence it is not satisfiable, right, it is unsatisfiable. That we understood, right. So, you can do the proof of enumeration that I talked about, that you construct the formula and check all possible scenarios, and then you can actually show that yeah, this formula is not satisfiable because it is false under all scenarios. Alternatively, you can actually, this is the encoding that I talked about, you can actually use the deductive proof, where you have certain obvious rules in the propositional logic, right? And I will just introduce some of them. I will take a dedicated class to give you all such deductive rules, and I will actually take more complex example to show that how the deductive proof works and where is the difficulty. That will be in the next class. But for today's class, just to show you the glimpse how do I solve this problem of this prime number example that I have taken, I just use the 3 inference rules from the propositional logic. The first one is called modus ponens, which is quite obvious, is saying that if an interpretation satisfies F and if the interpretation satisfies F implies G, then the interpretation also satisfies G. So, here there is a line in between, right. The upper part is called antecedent and this is called consequent, right. So, this is quite obvious from this implication rule. It was saying that if this is true, P is true, then Q must be true in a implication, right. This is exactly kind of getting reflected here. Here saying that you have P F implies G. So, there is an interpretation I which is satisfying this, and this interpretation also satisfies F. That means this is effectively true, right, under this interpretation. So, and now it also satisfies this. So, to satisfy this, this also must be true, right. This is what effectively talks about that if an interpretation satisfies F and the interpretation satisfies F implies G, then the interpretation must satisfy G as well, right. So, it is quite intuitive. The double negation is quite understood. If the interpretation satisfies negation of F, then effectively means the interpretation satisfies F, which is quite obvious. And the contradiction says that if the interpretation satisfies F and it also satisfies not F, that means this is problematic, right. This is contradiction. It cannot happen that under one interpretation the formula is true and false at the same time. This cannot happen. So, it means that such interpretation does not exist, right. And we will actually use this contradiction to prove whether the formula is satisfiable or not, right. So, we have 3 formulas here: A implies B in my case, not A and not B, right. This is what I have encoded, right, previously. So, these are the 3 formula I have encoded which I have discussed here, right. So, I have to check whether this F1 this conjunction of these 3 formula is satisfiable or not, and I am going to use these 3 rules. Okay. I will start with this. Say I have A implies B, this is the premises, this is already I have given, and I also have the premises is not A. Now, here I can use the double negation rule, which is if not A, if I satisfied not A, it means I satisfies A. So, from here I can actually say A is true, right, from the number 2 and the rule of double negation. Now, I have this A is true and A implies B is true. So, I can use the modus ponens, right, where I say that if I interpretation satisfy F and interpretation satisfy F and G, then it also satisfies B, right. So, here I have A and A implies B. So, I will take the 1 and the rule of modus ponens, and then from there I will get this also satisfies B, right. Now, I will use the contradiction. I have B is true here and not B is the third premises, right, that not B is also true. So, B the interpretation satisfy B, interpretation satisfy not B. So, this is a contradiction, right. So, that means I have shown that this situation cannot happen and it is not satisfiable, right. So, this is how the deductive proof works, but I will take a complete different class where I will take multiple examples and all deductive rules to show that how things works in more detail. Okay. I will conclude today's class with another interesting example of encoding. So, you need to know how do you effectively encode a practical problem into a satisfactory problem. So, that is the most interesting part. As long as you can do that, you can use some solvers or some tool that can actually check whether the formula is satisfiable or not, right. We have already different SAT solvers which we will be discussing in detail in this course, where we show that how the algorithm works. But to model your problem into this problem, you need to know how to encode that, right. Unless you are not able to encode that into a satisfactory problem, you cannot use these tools, right. So I will take a simple problem and show that how I can encode this into an satisfactory problem in propositional logic. Okay. So, the problem is called seating arrangement problem. Okay. You assume that there are 3 chairs, this is the left side, this is right, and this is the middle one, right. So, you have 3 chairs and you have 3 guests, and you have to give them seat there, they are going to sit there. Okay. Let us say you have 3 friends, Amit, Sukanto and Farhan. You have 3 friends and they came here and they want to sit in this chair. They can sit any chairs logically, but let us say there are some constraint. Okay. So, you have Amit, Sukant and Farhan. Let us say the constraint was says that Amit does not want to sit near to Farhan for some reason, maybe they do not like each other or whatever it is. So, Amit does not want to sit near to Farhan, and Amit also does not want to sit left in the left chair. Okay. He does not want to sit there, and Sukanta does not want to sit in the immediate right of Farhan, just immediate right of Farhan. So, now this is the problem, right. So, you have to tell who will sit in which seat, right. This is the, under this constraint you have to tell the exact sitting position of these 3 friends, right. That is the problem you have to solve. The first of all, to model this problem into a propositional logic, you need to identify the propositional constant, right. What are the propositional constant you need here? So, here you can see that there are 3 chairs, 3 persons, right. So, there are 9 possibilities effectively, right. Anybody can sit any of this and that way, right. So, there are 3 persons, 3 seats. So, it is 3 into 3, there are 9 possibilities. So, effectively you need 9 propositional constant, right, to encode this. So, what are the encoding? So, let us say I have assumed x I j, right. It is 1 means person I sits in chair j. Okay. Here I and j is basically I is 1, 2, 3, j is 1, 2, 3. These are the possibilities. Okay. And this is 0 otherwise. What does it mean? It means that if say x, so let us say x 1 1 equal to 1, it means what? Amit sits in chair 1, right, because I assume Amit is 1, Sukant is 2, Farhan is 3. If say x 3 2, what does it mean? Farhan sits in chair 2, right, and let us say x 2 3 equal to 0, it means Sukanto does not sit in seat number 3. So, this is how I identify my propositional constant. So, obviously you can understand here there are 9 possibilities, right. I can be 1 2 3, j can be 1 2 3, right. So, these are the propositional constant I have to encode this. Okay, this is what I talked about here. Now, let us see how can I encode this one. Amit does not want to sit near to Farhan. What does it mean? Say Amit does not, so if Farhan say sits here, right, so Amit will not sit here. If Farhan sits here, then Amit will not sit here, right. These are the 2 cases. If Farhan sits here, Amit will not sit here, but if Farhan sits here, Amit will not sit this place or this place, right. You got the point, right. So, that means if that situation happen that Farhan cannot sit here, right, then Amit has no chair to sit because he has to sit in one chair. So, this effectively says that Farhan cannot sit in the middle seat, right. So, how do I encode this? Is this. So, it is saying that if say Farhan sits in 1 2, this is Amit, 1 is Amit, right. So, it is saying that if Amit sits in the middle seat, right, you have this is the middle seat because 2 is the middle seat. So, Amit is sitting here. Then implies Farhan will not sit here or here. So, not of 3 1 and not of 3 3, right. So, 3 means Farhan, this is the, I think near to Farhan, right. So, I just explain in different way. So, if Amit sits here, Farhan cannot sit these 2 places because he does not want to sit near to this. So, that is what is encoded here, right, that Amit sits here means 3 means Farhan. So, not of 3 1 he will not sit here and not of 3 3 he will not sit here, and this is the other scenario. Here it says that if Amit sits either here or here, right, 1 1 or 1 3, right. So, if if Amit say sits here or here, that means Farhan cannot sit here, right. So, this is what not 3 2, right, Farhan is 3. So, Farhan cannot sit here, this cannot happen, right. So, this is how I encode the first one, that Amit does not want to sit near to Farhan, okay. And then the second one, probably I will repeat this one more time. Here I say that if Amit sits in seat number 1 or 3 implies Farhan cannot sit in seat number 2, right. Similarly, it says that if Amit sits in seat number 2, Farhan cannot sit seat number 1 or 3, right. This is how I encode this. Second one says that Amit does not want to sit in the leftmost chair, which is quite obvious, right. So, x11 is not true, right, x11 is not true, because he does not want to sit in this chair, right. So, this is understood, and the chair number is 1, 2 and 3, right. This is how I just give the name. Now, the third one is Sukanto does not want to sit immediate right of Farhan. What is the scenario here? So, if you see does not want to sit immediate right of Farhan. So, there are two possibilities here, right. So, if I clean it here. So, the possibility one is that Farhan sits here, right. So, Farhan sits here, then Sukanto will not sit here, right. Sukanto will not sit here, and if Farhan sits here, Sukanto will not sit here, right. There are two possibilities effectively, immediate right of Farhan. So, it says that if Farhan sits in seat number 1, Sukanto will not sit in seat number 2, right, or if Farhan sits in the middle seat 3 2, Sukanto will not sit in the last seat, rightmost seat, Sukanto will not sit in seat number 3, okay. So, you can clearly see that how do I model these English sentences using propositional logic. So, I have now 3 formulas, right, C1, C2 and C3, these 3, and I have to check what is the value of this 9 variable that satisfies this, right. If there is some assignment, then I will say this that is the correct solution, and that will be their sitting arrangement, right. But there is this constant is not only sufficient to get solution. What about if everybody sits, have you mentioned here that all of them cannot sit in one seat, right, or one cannot occupy more than one seat, right. So, those are the things are not mentioned here, which we understood obviously, but if you think about a SAT solver, he just tried to find out the value of these 9 variables, right, that satisfies. So, if you do not add those kind of constraint, what might happen that it might give you solution like that Amit and Sukanto sits in seat number 2, Farhan sits in seat number 3, right. So, that kind of solution might come. So, we have to add further constraint so that those scenario does not arise. So, what are the constraint you have to add? That each person at least get one seat, right. It is not the case that none of them get a seat. You have not mentioned that earlier. You have just added 3 constraint where you say the restriction who does not want to sit where, but you have not said that everybody has to get a seat, right. How do I encode that? Is the formula this. So, this part saying that x11, x12 and x13. You remember this 1 is basically person 1 and this 1, 2, 3 is the seat number. So, what I am saying here that x11 or x12 or x13, what does it mean? At least one of them must be true, then only this formula will be true. That means it says that at least the person 1, which is Amit, gets one seat, right. This part actually ensures that Amit gets at least one seat, right. So, that means they will get at least one seat, but this can be that it get more than one seat as well, right, because this is or all of them may be true, 2 of them may be true, then also this is true, but at least one of them should be there. So, that means he will place at least once. So, I have to add some further constant to make sure that he is not getting 2 seats. So, that will be the next constant. Similarly, this is for person 2, Sukanto, this is for Farhan. It says that Sukanto gets at least one seat, right, 2, 2, 2. So, 2, 1, 2, 2, 2, 3. That means either Sukanto is sitting in seat number 1 or seat number 2 or seat number 3. At least one of them must be true. Similarly, it says that Farhan sits either seat number 1, 2 or 3. Okay. So immediately the next constant is that no person is placed in more than one place, right? How do you encode that? That is a little bit tricky. Earlier I saw that they get at least one seat. Now I am saying that they cannot get more than one seat. So if you combine these two, they get exactly one seat, right? So what I am writing here is that you see the first part of the formula, right? This is for person 1. What I am saying that not of x11 or not of x12, it is true. That means what? At least one of them is false, right? That means at least Amit is not sitting either seat number 1 or 2, right? So the first part, this says that Amit is not sitting in either seat number 1 or 2. At least one of the place he is not sitting, right? Then I am saying he is not sitting at least one of the place of 2 and 3, and this is what I am saying, he is not sitting seat 3 and 1, right? So he at least one of 1 and he is not sitting in 1 or 2. So he is at least one of them is false, right? To become this is true, either a not of x11 is false true, or this is true, right? So that means x1 is false, right? Or x12 is false. That is what I am saying, that means he is not sitting in x11 or x12. Now I am saying ki one of the two places he is not sitting 1 2, then 2 3 and 3 1. To satisfy all of them, you need at least two of them should be false, right? What means he is not occupying more than one seats. Did you get the point? So I am repeating again. So this is saying that he is not sitting 1, not sitting 1 or 2. This one saying that 2 or 3, right? And this is saying 3 or 1. So now all of them is true, right? So to make all three of them true, at least say let us say if one is true, this and this will be done, right? Then at least 2 or 3, one of them should be done. So that now 2 of them is true, right? So 2 of them is basically false. So if 2 is true here, then this and this will be true. Now 3 or 1 has to be 1 true, right? So this way, this actually ensures that at least 2 of them sits, he is not sitting, he is sitting exactly one place. The next part is for person 2 and the third part is for person 3. So it is saying that second part is saying that Sukanta is not sitting more than one place. Third part is saying Faran is not sitting more than one place. Similarly, you have to add the constraint here that each seat is occupied by exactly one person, right? Person 1, everybody is sitting in one place, right? It may happen that person 1 is also sitting in one seat number 1, person 2 is also sitting in seat number 1, person 3 is also sitting in seat number 1, right? Then also that is true, because everybody is sitting in one place, they are not sitting in two places. But I have to also ensure that one place is not occupied by two persons. So same way I am doing it. Now I am basically varying the person but keeping the seat intact, right? So this is 1 1 or 2 1, right? 2 1 or 3 1, 3 1 or 1 1. What does it mean? From this it is saying that seat 1, for seat 1, either person 1 or person 2 is not sitting, right? So this x 1 1 or 2 1. So either person 1 or 2. Then this says that either person 2 or person 3 is not sitting in seat 1. In seat 1. Then this says that person 3 or person 1 is not sitting in seat number 1. So if you combine these 3, it effectively will say that only one of them is sitting in seat number 1. And now that this is for seat number 2 and this part is for seat number 3, right? So this is how I encode the entire thing. So this is sufficient now, right? So now what you have to do, you have to just check satisfiability of C1 and C2 and C3. This is the initial constraint, and then identify 3 more constraints, C5 and C6. This is my formula, right? So I have to check whether this formula is F is satisfiable, right? So here because there are 9 variables, there are 2 to the power 9 possibilities, right? So 2 to the power 9 is 512. So you can actually create a 512 scenarios and check is there any solution for this, right? Alternatively, you can also use the deductive rules I talked about, but this is tricky because the formula is quite big, right, and the number of variables is also more. So, we learn more about how to show whether this formula is satisfiable or not, or whether your guest will get a seat in your probably invitation. That we'll discuss later, because we will discuss the more satisfactory problem in subsequent classes. But to summarize today's class, we have learned the syntax and semantics of propositional logic. We have learned how to show the satisfactory of a propositional formula, either by proof of enumeration or by proof of deduction. And then we have taken two small examples, one is for prime number and one is for the seating arrangement, and so how do you actually encode the problem into propositional logic problem or satisfactory problem of propositional logic. Okay. With this I conclude today's class. Thank you.